Yo, welcome back. All right, we're going to talk about two things today: average rate of change and instantaneous rate of change. I'm kind of just get right to it. So, to find the average rate of change of a function y equals f of x over some closed interval a b, it's actually pretty simple. All right, you really just figure out the slope. So you're like, what the heck am I talking about? You did this actually in the algebra days, right? Change in y over change in x is how we compute slope. So if this is what I'm talking about here, if this is the point, say b comma f of b, right? And this is the point a comma f of a. If I want the average rate of change of this function over this closed interval, I just find the slope of the line that goes through these 2 points. And that line has a name. It's a secant line. So to do that, it'd be change in y, so f of b minus f of a all over b minus a. And that's it. That's the formula, right? Sometimes we'll abbreviate that m for slope, subscript secant, or just sec for secant, all right? And we have to understand that the slope of a secant line represents average rate of change, and you're going to see me refer to it as AROC a bunch of times, over some interval AB. So it's honestly, it's not the most craziest thing in the world to think about it this way, because think about average rate of change in general. Say you go on a car trip and you cover 100 miles and you do that in a lapsed interval, in a lapsed time of 2 hours, right? So the change in distance covered of 100 miles divided by the change in time elapsed, which would be 2 hours, right? Do 100 miles in 2 hours, your average speed is 50 miles per hour. And you got that by doing 100 divided by 2. So when we apply this now to just functions in general, it's just basically slope. It's the slope of a secant line. All right, so now what I'm about to do with you is basically the same exact thing, but we just label the picture differently. So like here, I had my function, this was A, this is B, that was my closed interval AB. Well, what if instead of calling the interval AB, I call it AX, where I'm now labeling this point to the right endpoint is X, because maybe it's allowed to vary. Well, nothing changes, right? So again, if I want the average rate of change now over the interval AX, right? It's still slope of a secant line. It's still the slope formula, change in y over change in x. In this case, change in my y values would be f of x minus f of a over x minus a. So I'm not really doing anything differently, right? It's the same exact problem. I just decided to label this point x instead of b. You're like, well, why are you doing that? Well, I'm doing that because you're going to see this expression in other contexts with these exact letters x and a. And we have to know that now when we see this little difference quotient here, right? It's a quotient because it's divided by, and there's subtraction in it. So we call this a difference quotient. This difference quotient represents average rate of change. All right, we'll do it one more time where I'm not going to change anything other than how I label the picture. All right, so now maybe I have A, but instead of calling this B, or instead of calling this X, I call it A plus H. So it's A plus some value. Now maybe I should make a note that in this particular picture, H is positive. It's greater than 0. That's why A plus H is to the right of A. But you'll see later on that it doesn't have to be. I could draw the picture the other way, but that doesn't matter. All right, so now what is this point, just for emphasis here? Well, the x value is a plus h. The y value is going to be f of this, right? So if this is my input, my output is f of that, which I wrote right here, just f of a plus h, okay? And then obviously this point is still a comma f of a. And so now if I want the average rate of change, and this is what I'm going to write here, the average rate of change over, now I'm calling the interval a to a plus h. Again, that's just m secant. Again, it's just slope of the line. And again, now it's going to be change in y values. So f of a plus h minus f of a all over a plus h minus a. But now what happened here, which is a little interesting, is you can simplify this, right? So these a's are going to sum to 0. So you end up getting here that our average rate of change is going to be f of a plus h minus f of a all over just h. So it's a little bit weird when you see it this way because you don't see the subtraction in the x's because I kind of canceled out those a's. They sum to 0. All right, but it's still a difference quotient. It still represents our difference quotient simplified. All right, and it still represents average rate of change. So in all three of these examples, whether I labeled AB, AX, or A plus H, they're all slope formulas. They're all finding the slope of a secant line. And the big takeaway today is for you to understand that to find the average rate of change of a function over an interval, you simply take the slope of the secant line over that interval. And this is just me here wrapping up what I just went over with you. All right. Now, I put this one separate from these guys because, quite honestly, this is the one that we're going to really mainly use when asked directly, what's the average rate of change of a function over the interval AB? Well, then I'm going to say, what's the formula? And you can say delta y over delta x, but basically it's f of b minus f of a over b minus a. All right, so that's average rate of change. So now what do I want to do next? Well, now I want to talk about instantaneous rate of change. And this is going to seem a little weird to you. But if average rate of change represents slope of a secant line over an interval, then what does instantaneous rate of change? How is that represented? And you can see my picture here. It's actually represented by the slope of a tangent line. All right, so let me show you a little Desmos animation here. So this red line here would be the secant line. The slope of that line would represent the average rate of change over this interval here, right, between these 2 points. This green line is a tangent line. The slope of that line represents the instantaneous rate of change at this point right here. So you're like, all right, so to get average rate of change is pretty easy. It was that difference quotient. How do you get instantaneous rate of change at a point? Well, you can't use the same formula. So in other words, let me go ahead and get rid of my point here and my secant line. If I want to find the instantaneous rate of change here, well, I can't use that delta y over delta x formula because it's just at a point, right? The only point I have on this curve is that point of tangency. So in theory, the change in y and the change in x, they're both 0, right? So how do you do it? Well, we start off by approximating the slope of that green line. And the way I can do that is I can use the slope of the red line to approximate it. So I can say, hey, I can calculate the slope of this line because I could just do change in y over change in x, right, with these 2 points. And that would represent an approximation of the slope of the green line. Now, you might be saying, well, that's a pretty stinky approximation. They don't even look like they're remotely close. So my question to you would be, well, how can I make the approximation better, right? Maybe pause the video and think about that. And hopefully you come back and you say, well, just make the interval smaller. In other words, take this point and move it closer to that point. If I move the point closer, say right there, now the slope of that secant line is a little bit closer to the slope of the tangent line. How can I do better? We'll keep making it go closer and closer and closer to that point, right? And you're like, wow, now there's not much difference. And in fact, as I get closer and closer to the point, there's not going to be any difference between the secant line and the tangent line. So in other words, that tangent line kind of occupies this limiting position of me driving this point, right? So I have 2 points to get the slope of a secant line. As I drive that right point closer to the left point until they become 1, I end up getting the slope of that tangent line. So that should sound like it to you an awful lot like a limit, okay? All right, so that's kind of the visual. Let's go ahead and derive this thing now. All right, so there's 2 ways that we can derive it, and we can use basically the last 2 pictures that I showed you above to do this. So let's pretend like we're using the first picture, the second picture. So I have this y-axis, right? I have an x-axis. I have a function, y equals f of x, and I'm interested in the slope of the tangent, right? But I want to do it by first approximating by using the slope of the secant line. Okay, so this would be the secant. And in the visual I just showed you, I want to take this point, move it to that point. So let me label this stuff. We're going to call this A. We're going to call this X, okay? That would mean that this Y value is f of A, and that would mean that this X value, this Y value here is f of X. So watch what I do. So you're like, all right, we'll start with the slope of a secant line. You know how to do that. That's just going to be f of X minus f of A over X minus A. Now that by itself gets you the slope of the secant line. But remember now, to get the slope of the tangent line, right, I want to bring this point closer and closer and closer here. So now what does that mean? That means this right endpoint, X, has got to go to what? It's got to get closer to A. So if I take the limit as X goes to A, I now get the slope of the tangent line. And what is the meeting of the slope of the tangent line? It's the instantaneous rate of change of this function at the point X equals A. All right. So my instantaneous rate of change, IROC, at X equals A can be expressed as the limit of this difference quotient. That's pretty cool. All right. Let me do it one other time because you see it another way, kind of famously. All right. So I'll draw the same picture, and I guess I probably should have had these drawn for you already, but whatever. So here's A plus H now. I'm just going to label it a little differently. Do the same thing. I'm going to kind of draw my function. Go ahead and put in that secant line first. So there's my secant. Here's my tangent. And I'm interested in finding the slope of that. This y value here is f of a. This y value there is f of a plus h. So now how do I represent the instantaneous rate of change or the slope of the tangent line at A? Well, I start off the same way. Let me start with the slope of the secant line. Well, we did this above. The slope of the secant line was f of a plus h minus f of a, right? That's change in y values, all over a plus h minus a. But as you saw above, we summed those, the a's to zero. So this right here by itself represents the average rate of change over this interval. So now what do I need to do? I need to bring a plus h closer to a. So this point has to get closer to that point so that my secant line occupies that limiting position of the tangent line. So now I don't write as a plus h goes to a, kind of like what I did here. I do it by just simply saying the limit as, maybe you can figure it out. What do I need to do to h to drive a plus h to a? Hopefully you're saying just drive h to 0. As h goes to 0, right, then this point gets closer to that point, and here I go. I get what we call the slope of that tangent line, or the slope of that curve there. And again, that's going to be the instantaneous rate of change at x equals a. All right, so this is actually kind of good news for you because the average rate of change formula is kind of built into the instantaneous rate of change formula. You just have to take the appropriate limit to drive the right point closer to the left point to get the instantaneous rate of change. Now, I'm using right point and left point, but in theory, it could be a little bit different than that, but for all intents and purposes, that's going to work for now. All right, so what's the summary here? And I'll just kind of read this so you can pause it and read it. The slope of the secant line represents average rate of change, which sometimes I'll just write AROC, right? Over an interval. That's kind of the key. When you're finding average rate of change, it's about being over an interval. The slope of the tangent line is going to represent instantaneous rate of change, and that is at a point, right? So instantaneous rate of change occurs at a point where average rate of change occurs at an interval. So now this is kind of important here as well. It says we can always estimate the slope of the tangent line, right? The instantaneous rate of change, those are analogous, using slope of the secant line, or the average rate of change, right? And the tighter that you make that interval about the point, the better the estimation will be, okay? All right, so that's instantaneous versus average rate of change. Next video, I'll actually go ahead and start these problems right here.